All right. Let's do a quick problem. Have you guys work on this? You can work with your neighbor. So we're going to have a galvanic cell, working galvanic cell, based on this reaction given, and some half reactions. I want you to calculate the cell potential. Just give you a minute or so. All right, so our standard cell potential is going to be equal to standard reduction potential of the cathode minus the standard reduction potential for the reaction at the anode. Okay. You need to figure out which reaction is occurring at the cathode and which is occurring at the anode. You can see in our overall reaction that we have the aluminum ion on the reactant side. And so this reaction is occurring as written. Okay, aluminum solid on the product side. The magnesium reaction then is occurring in the opposite direction. So if we reverse this, we'll have magnesium solid. This is our oxidation reaction. Okay, we're losing our electrons. So that's occurring at the anode. Does everyone see how that's going to work? Okay, so this is our reduction. So we should end up with 1.66 volts minus negative 2.37 volts. And we'll get 0.71 volts. So it's a positive number. That's good. Yes?
So for the top, so it's
Did I?
positive?
Nope. Okay. I just missed it. Yep. Okay. Other questions? Yes? You don't flip the sign even though you flip the equation. And it's convention based on this reaction. You might find other sources that tell you otherwise. Stick with one plan. Anything else? The other thing is this, when I didn't actually go through and balance the equations. Okay, so if you look at, we would have 3 electrons and 2 electrons in the 2 different half reactions. If you were to balance that, you'd have to go through and multiply each of those by a factor. It doesn't matter for this question because our cell potential does not depend on the number of electrons that are transferred in the reaction. That's not always as the one we just used here. Okay, be the case though. So let's start bringing in the concept of free energy and redox reactions. So free energy, as we had talked about before, is the energy that's available to do work. And when you have an electrochemical reaction, you're transferring electrons. Of course, you're going to want to make those electrons do work. So, excuse me. One of the things your book sort of leads to next is a more general way of writing the equation we've just been working with, the standard cell potential equation. What I want to stress is that you don't always have galvanic cells. So you may see an equation where it's just the standard potential is equal to the standard reduction potential for the reduction process minus the standard reduction potential for the oxidation process. This is the same equation, just slightly different nomenclature, so you're not stuck in the thought that it's a galvanic or voltaic cell. The other thing that's important to note is that we've been focusing on coming up with cell potentials that are positive, because those are the reactions that will happen spontaneously in a voltaic cell. Those are the working voltaic cells, working galvanic cells. So a positive value of positive value of the cell potential is a spontaneous process. A negative cell potential is a non-spontaneous process. The reason is that the Gibbs free energy, delta G, is proportional to the cell potential minus Nf E naught, or standard potential. I will most likely be speaking in terms of using the word potential, but I also want you to know that your book tends to use electromotive force. So the force that comes about when electrons are flowing. I'm just more accustomed to saying potential, so if I'm trying to switch because I know it's what your book uses. But EMF electromotive force. So the relationship is that the free energy is equal to minus N, where N is the number of electrons. F is Faraday's constant, right here. So 96,485 coulombs per mole. Okay. This is another term. If you convert coulombs to joules per volt, it's 96,485 joules per volt mole. And that's the quantity of electrical charge on 1 mole of electrons. So N is actually a mole of electrons, but the number of electrons transferred in a reaction. And you can see that if our cell potential, or our standard potential, is a positive value, we're going to have a negative value for our delta G, which is a spontaneous process. Okay. Now that we can relate our Gibbs free energy to our standard potential, we can relate our standard potential to an equilibrium constant K. So we just saw that delta G is equal to minus NFE. But we also know from chapter 19 that delta G is equal to minus RT natural log of K, the equilibrium constant. So we can set these equations equal to each other. We'll have minus NFE naught equals minus RT natural log of K. If we divide both sides by minus NF, we'll end up with the standard potential is equal to R times T over N times F times the natural log of K. You'll often see this equation written in the log base 10 formula, so we can convert to that. The definition is that 2.303 log of x is equal to the natural log of x. So if we substitute this in for here, we'll get our E standard potential is equal to 2.303 R times T over N times F times log of K. And because R, T, and F are going to be constants, and we could say we're always going to be for the most part, always going to be at 25 degrees Celsius. We can take those all to be one constant. So that at 25 degrees Celsius, 2.303 times R times T over F is equal to 592 volts. So we'll have the standard potential is equal to 0.0592 over N times the log of K. So we're able to relate our cell potential, or our standard potential, to an equilibrium constant as long as we know the number of electrons transferred in a reaction. Okay. Questions on that? Yes?
Which one of those equations did they give on the
I believe, that's a good question. If, might be this one? I'll have to check, but it's available on the practice midterms. I haven't looked at that yet, I'm sorry. I haven't looked at the equations. Okay. So let's work through an example problem. Let's say we have a galvanic cell with the following half reactions. And we want to calculate delta G naught and the equilibrium constant. Let's break this up into some stepwise plans here. The first thing we're going to do is write the overall cell reaction. Now, I haven't told you what the overall is, of course. That's why we're going to write it. The only thing you know are the standard reduction potentials. But we also know that for a working galvanic cell, the standard cell potential must be positive. So looking at our equation, standard cell potential equals E naught reduction at the cathode minus E naught reduction at the anode. The only way for this value to be positive is if the copper reaction is our reduction reaction, and the chromium reaction is our oxidation. Okay, so then we would have reduction potential of 0.34 volts for the copper. So this is reduction. This will be oxidation. We'll need to rewrite that. Minus negative 0.74 volts. And we'll end up with a cell potential of 1.08 volts. So everyone see that? Okay. So given this, let's rewrite our half reactions with the correct formulations. So we're going to have the chromium solid forming chromium 3 plus, aqueous plus 3 electrons. So oxidation is loss of electrons on the product side. And then our copper reaction will occur as written above. So the copper 2 plus 2 electrons forming copper solid. Okay, so you can see that we didn't need to do that. It said we won't need to balance equations to get our cell potential, but we do need to do so in order to get an overall. We've got 3 electrons in the chromium half reaction. We've got 2 electrons in the copper. So if we multiply copper by 3 and chromium reaction by 2, we'll be able to get cancel out our electrons and then write an overall reaction. So we'll have 2 chromium plus 3 copper ion plus 6 electrons, forming 2 chromium ion plus copper solid plus 6 electrons. Okay. Electrons, of course, would cancel, and that's your overall reaction. But it's important to note that 6 moles of electrons are transferred. We're going to need that in order to calculate delta G and K. Everyone okay with that? All right. So part 2, let's calculate delta G. And we're going to use delta G equals minus NFE. And we just said that N is equal to 6 moles of electrons transferred. F is a constant equal to 96,485 coulombs per mole of electrons. And we just calculated our cell potential, which was 1.08 joules per coulomb. So basically, plug and chug. Delta G naught equals minus 6 times 96,485 times 1.08. Moles of electrons will cancel, coulombs will cancel. We're going to be left with joules. We'll get minus 6.25 times 10 to the 5th joules for delta G. So very spontaneous reaction, right? Very large negative number. Right? Questions on that? Okay. So the third step then is to calculate the equilibrium constant. We have 2 options for this. We can use delta G equals minus RT natural log of K. That's from chapter 19. Or we can use the equation we just calculated, or just derived. The potential, standard potential, is equal to 0.0592 over N times log of K. Your choice, but I'll try both. Okay, so if we do delta G equals minus RT ln K, we'll take our delta G we just calculated, minus 6.25 times 10 to the 5th joules, equals minus R, 8.314, times temperature, 298 Kelvin, ln of K. Excuse me. You should get 2.52 times 10 to the 2 equals the natural log of K, or 252. So if we take base natural log, we'll do our K is equal to e to the 252, which is a very large number that you can't actually calculate, probably on your calculator. So what's that say about equilibrium? Reactant favored or product favored? Product favored, right? Large K. If we do use our cell potential, okay, again, we have 6 electrons transferred. Our cell potential was 1.08 volts, 0.0592 volts, 6 electrons, log of K. Multiply, divide, math magic, you get 109 equals log of K. And so K, oops. Oh, okay. K is equal to 10 to the 109. Do we get the same answer? You should, right? Here we go. Here we go. This is fun. 2.303. Oops. Oh, wait. 2.303. There it is. .303 log of x equals natural log of x. So these are off by that factor, 2.303. Okay. So you do get the same answers. Both are too large to actually calculate. Before I move on. All right. Okay. Do you have questions on that last problem? So, how are the standard cell potential, or standard potential, doesn't have to be for a galvanic cell, delta G and K affected by an overall reaction if we're multiplying by a factor, for instance? So let's say we take our copper and chromium reaction where we transferred 6 electrons and we multiply the whole thing by 2. We know, we talked about this before, that our standard cell potential is not affected. So it's not affected by the coefficients in your overall reaction. And you can look at your equation for calculating E cell, standard reduction potential at the cathode minus the standard reduction potential at the anode. There's no N showing up in there anywhere. But for delta G, we should see, if we multiply by a factor, a whole number, not a fraction. If we multiply by 2, for instance, we should see an increase in delta G. And that's because delta G equals minus NF E. And it's affected by N, the moles of electrons. So if we multiply this equation by 2, we have to multiply the electrons by 2, which means we have more electrons transferred, which means delta G will increase. Well, larger magnitude. Same with K. K will increase because N increases. And we can see this in E cell, or standard potential is equal to 0.0592 over N log of K. So these delta G and K are extensive properties. Your standard cell potential or your standard potential is an intensive property. All right. So these, the equation that we just calculated just determined where we look at how the equilibrium constant is affected by the cell potential. All of that is at standard conditions. And so if we're in aqueous solution, that's a 1 molar solution. If we have gases, that's 1 atmosphere. But it's not very often that we're going to be strictly looking at 1 molar solutions of things. So we need to be able to calculate cell potentials or standard potentials under non-standard conditions. So what we find, and if you think about how a battery works, just very loosely, we're going to have a potential for the battery to do work. Have you ever measured with a voltmeter the potential across the battery, the leads? So you can check if it's charged or not, if you use rechargeable or things like that. Anyway, as the battery is used, the potential decreases. And what we find is that it will decrease until the cell is dead, the battery is dead. And that's because the concentrations of reactants in products are changing, that we see this change in the potential. What we'll also find is that a battery is dead when the reaction reaches equilibrium. So let's look at calculating. How will we calculate this? So we know from chapter 19 that the free energy, delta G, is equal to the standard free energy plus R times T times the natural log of Q. We also know now that delta G is equal to minus NFE. And this could be standard or non-standard. So you can have our not symbol or not. Hilarious. Okay, so we can now plug in minus NFE for delta G. So minus NFE equals minus NFE naught plus R times T times the natural log of Q. And we can divide everything by minus NF. And so we'll end up with, the potential is equal to the standard potential minus R times T over N times F times the natural log of Q. And we just saw how we can relate natural log of something to the log base 10. And if we remember, we used R times T over F. We said that was a constant. Same story here. Oops. So at 25 degrees Celsius, 2.303 times R times T over F, still equal to 0.0592 volts. So we can substitute that into this equation. I'm also going to write convert to log base 10 of Q. E is equal to E naught minus 0.0592 over N times the log of Q. Does anyone know why we keep converting from natural log to log base 10? No. It's actually kind of a fun reason. Mostly the answer is it's because this is old school. Before 1970, people didn't have calculators carrying around with them, but they could do large math problems. And so log base 10 tables were a thing that you would carry around with you. Natural log was a little bit more challenging, so people would have log base 10 tables and slide rules, and that's how they would do their calculations. So that's where this is based in. It's actually easier to do a log base 10 calculation. So that's why we're converting everything. And so you'll see equations like this. So this is referred to as the Nernst equation. I know this one will be on the exam. Okay, so this will allow us to figure out the cell potentials for any reaction with concentrations other than 1 mole of every.
A problem says it happens at like 30 degrees Celsius. Can I use that then?
Right. If it happens at a different temperature, you'd have to use the equation where you're multiplying RT. You'd have to use this. Yeah.
Is that given to us on the exam?
You know what? Now I'm questioning. I'm pretty sure you get the one with this.
Okay.
I'm not sure now.
Okay.
Yeah. Other questions? Mole per liter anyways. The other thing that's kind of neat here is that, oh yes, sorry.
So if
Okay. So we looked at a lot at Le Chatelier's principle when we started talking about equilibrium in chapter 15. It carried on through common ion effect and buffers and things like that. Well, it still applies here as well. So let's look at a reaction where we have solid aluminum plus manganese ion forming aluminum ion and manganese. The cell potential for this reaction is 0.48 volts. So that's saying is that as the reaction runs in the forward direction, 0.48 volts are produced. Okay? So if we increase the concentration of reactants, let's say above 1 mole per liter, Le Chatelier says that we should be able to produce more products. So if we increase the concentration of reactants, we produce more products to regain equilibrium. Okay. And when we're producing more products, electrons are also going to be part of this, right? They're going to be moving more. So we'll have a greater cell potential. So we'll see an increase in E cell. Okay, so that's increasing the concentration of reactants, leaving the concentrations of products the same. If we increase the concentration of products, okay, Le Chatelier tells us, of course, we're going to need to make more reactants in order to regain equilibrium. So in that case, E cell is reduced. So that's a nice way of thinking about this, just in terms of Le Chatelier's principle, but we actually calculate quantitatively what's happening using the Nernst equation. So let's take a look at our reaction. And let's say we want to find this cell potential if we have a manganese 2+ ion concentration of 1.5 molar, and the aluminum ion concentration of 0.2 moles per liter, 25 degrees Celsius. Why don't I have the concentration of the other species? Yeah. They're solids, and they're not going to play a role in our equilibrium constant, so we don't need to worry about those. Thank you. Okay, so first thing we need to do, because the cell potential is dependent on the number of electrons transferred, we need to determine the half reactions. So, how much time we have left? 5 minutes. I kind of want to get through this, so I'm just going to keep going here. So for our half reactions, we know we have 2 aluminum solid, and it's forming 2 aluminum 3+ ion and 3 electrons. And then for the second half reaction, we're going to have 3 Mn2+ aqueous forming plus 2 electrons, forming 3 Mn solid. The other thing I should point out here, I think your book does a really terrible job of including equilibrium arrows for this part of the course. There is equilibrium going on. That's why we have a K. All right. So I'm probably also going to be a little sloppy with equilibrium arrows, but there is an equilibrium going on in this reaction. All right. Okay, so we need to balance our half reactions so we can add them up. We have 3 electrons transferred in our first half reaction, 2 in our second, so we need to multiply the top by 2 and the bottom by 3. And sum these up, and we'll see that we're going to have 6 electrons transferred. I'm not going to worry about writing the overall reaction. Don't technically need it, we just need to know the number of electrons transferred. Questions on that? Yeah?
Why isn't it 6 electrons
6 electrons. Oh, this one?
For the first one that you were
Oh, okay. So I have 3 here and I have 2 here. So I'm multiplying by those factors in order to make them both 6. And then we can cancel them out. Yeah.
Wouldn't it already be 6 since there's 2 aluminums with 3 plus?
Oh, you're right. You're right. Yep, I just didn't take that into account. 3 Mn, 2 plus. Yeah, sorry guys. Anyway, 6 electrons transferred. Okay, 6 and 6. So then we need to plug everything into our Nernst equation. E cell is equal to the standard cell potential. So that's something we're going to need to calculate from our standard reduction potentials. Minus 0.0592 over N times the log of Q. And in this case, Q is going to be the concentration of aluminum 3 plus squared over the concentration of manganese 2 plus cubed. Okay, we're given our standard cell potential, so that's 0.48 volts. Minus 0.0592 over 6 times the log of 0.2 squared over 1.50 cubed. So we'll get 0.48 minus negative 0.02. And we should get 0.50 volts. And so we see an increase in the cell potential. And that makes sense because we've increased the concentration of the reactant and decreased the concentration of the product relative to 1 mole per liter. Does that make sense? All right, we'll stop here.